Hello, I'm Marcel Bilurbina. I'm going to give the ninth module of the Master Relational Design. And that module is called Custom Design, Processing and the Laws of Genetics. I'm from Barcelona. I studied architecture there, and after 8 years working at different architecture firms, I decided to study a master degree in digital arts at Universitat Pompeu Fabra in Barcelona. And that allowed me to understand in deep the digital fact. Learning the basics of programming and electronics was a great help to me to understand its consequences in architecture and design. My thesis project, an interactive design tool made with processing and based on the use of genetic algorithms, allowed me to better understand the invaluable importance of the use of procedural generation methods in design. Currently, I'm based in Barcelona, where I combine the work as architect and landscape architect with the realization of interactive audiovisual installations and teaching as a professor in the Master of Advanced Design and Digital Architecture at Elizabeth School and in the Master in Digital Arts at Universitat Pompeu Fabra, also in Barcelona. The teaching experience has been a great opportunity to consolidate and rethink about the new procedural methods to define architecture, as well as a very enriching personal experience. That's been a great opportunity to broaden my knowledge of key concepts as emergence, self-organization, and agent-based systems applied to design. Preparing the processing code libraries that the students use in the workshops has made me understand in deep how those form generation process works. Hello, the first thing that I would like to do as introduction for that course is to explain a little bit the reason of the title of the module, which is Customization, Processing, and the Genetic Laws. So I'm going to make a short description of each of the terms: customization, genetic algorithm, and processing. Customization may be defined as the process in which an individual or group appropriates a product and makes it their own. That means that the designers of a customizable product are designing a family of products and not an only object or product. So that means that they have to study a set of variables that the final user can change in order to adapt it to their needs. Until now, what is important is that instead of defining an object, what we define is a family of objects, a set of objects, or what is called in terms of genetic algorithms, a population of objects, individuals or phenotypes. So the task of the genetic algorithm designer will be to define that family that in terms of genetic algorithms is called the genotype or the DNA that will be able to achieve different configurations. The genetic algorithm can be defined as an algorithm that mimics the process of natural selection. What is an algorithm? An algorithm can be understood as a set of instructions or procedures that have some specific purpose. The genetic algorithms are computer algorithms based on the laws of genetics and natural evolution that emerge as a combination of contributions from mathematics, computer science, and biology. The conceptual basis of genetic algorithms is clearly inspired by the laws of natural evolution postulated by the biologist and naturalist Charles Darwin. These laws explains the evolution of species according to the concept of natural evolution where individuals better adapted to their environment are those with more possibilities to survive and to preserve the genetic information that characterizes them. This natural selection causes that the species evolves towards a better adaptation to the environment. The idea of creating optimization techniques based on natural selection mechanisms was introduced by John Holland and David Goldberg in the 60s and applied to solve combinatorial problems with high rates. The last term that I would like to clarify is what is processing. Genetic algorithms are inherent to the computing because in order to run them we need to make a huge amount of calculations because the genetic algorithm's logic has no end, so it has to be understood as an engine that is running continuously as a continuous loop of iterative operations that never stops. And the third reason why computing is inherent to the genetic algorithms is that in most of the cases the steps that have to be done needs the binary system, which is implicitly related to the computer logic. So to learn the logic of the algorithm is going to help us to understand the concept, because it's really linked to it. So, what is processing? As the creators of that project define it, processing is an open source programming language, an integrated development environment, IDE, built for the electronic arts, new media art, and visual design communities with the purpose of teaching the fundamentals of computer programming in a visual context and to serve as the foundation for electronic sketchbooks. The project was initiated in 2001 by Casey Rees and Benjamin Fry, both from the computational group at the MIT Media Lab. One of the aims of the processing is to act as a tool to get non-programmers started with programming through the instant gratification of visual feedback. The language builds on the Java language, but uses a simplified syntax and graphics programming model that simplifies a lot of the tasks. The aim of the course will be to understand the relation between natural evolution and customization process, and we'll see how the genetic algorithms may be used as a tool to help users to generate their own customized product according to their needs. As genetic algorithm designers, we will design an species, design, or genotype able to take different shapes or phenotypes. As I've already said, according to the principles of natural evolution, the individuals best adapted to an environment have more descendants, so they have more probabilities to transmit their genetic information. Assuming that premise, if we would be able to simulate a species and its evolution throughout several generations, we could make evolve the species towards a specific direction, changing the environment conditions. If we understand that the environment conditions are the user needs, we will be able to use a genetic algorithm as an engine for design customization. To design using a genetic algorithm engine implies the following steps. The first one is to learn to codify and decodify our species or design. What does codify means? Codify means to identify the parameters and variables that define the design. Identify which of those parameters are able to be modified and their ranges and the ranges they can keep, and translate those parameters into a chain of binary numbers which will define our DNA. In genetic algorithms, the DNA of a species has an only chromosome, which will be that chain of variables translated to binary. All the values these variables can have define all the combinations and final shapes or phenotypes that the species can achieve. Codify define the way these parameters are combined in order to produce a specific individual, a specific design, a specific object that can be evaluated. So now that we are able to codify and decodify our species design, we are going to see which are the steps that defines the algorithm itself. So the genetic algorithm, the first step, the first thing that we do when running a genetic algorithm is to create a random population of individuals. That means that we select, we define a number of individuals that defines the population, and we give them random values to their parameters and variables. So we have a combination of individuals with very different features. So once that, what we do is evaluate each of the individuals according to a fitness criteria. Fitness criteria means that we are going to evaluate if those individuals fit with the environment defined. That environment is defined according to a fitness function that will correspond to the user needs. So the user will be able to define which are the values of that fitness function. So once we have evaluated the individuals, that means that each of the individuals that defines the population have some score. So once that, what we do is the selection process. Selection process consists, there are many ways to do it. One is take all the individuals and copy them as many times as the score they got in the selection, in the evaluation process. So in that way, they will be, we call the place where we put all those individuals a matching pool. So in that matching pool, we'll have a lot of good individuals. So because the good individuals will be copied more times because they got more score, and we'll have few individuals with bad that doesn't fit with the environment. So, and once we have full our matching pool, we're going to select them by pairs, and we're going to apply the crossover and the mutation operators. So the crossover consists on taking two parents from that matching pool and to take one part of the DNA of that chain of bits of one parent and take another part of the DNA of the second parent and to join them. So in that way, we'll get a new DNA that will correspond to a child of those parents. So we're going to do that as many times as individuals we have. So in that way, we'll have the end a new generation of individuals. So once we have a new individual, we apply the mutation operator that consists on taking one of the bits that defines the DNA, the chromosome of the species, and mutate it. So if it's 0, take some of them, if some mutation rate is true, and change 1 0 by 1 1 or 1 1 by 1 0 if some random conditions are true. So once we have that new generation, what we do is apply the same functions to that new generation. So we evaluate them according to our fitness criteria. We select them, we select the best individuals, and we cross them and we mutate them. And we'll do that as many times as we need. So until we consider that the species has evolved and it has reached our goals. So now I'm going to show you one similar project that consists on the design of a table using genetic algorithms as in Jane. So here you can see the interface defined, where we can see the whole population using that consists on 12 individuals. Yeah, that corresponds to a third generation that, as I explained, it's a random generation where all the genes, all the variables get random values. So therefore, there are tables with 3 legs. There are some other with 7 legs. There are some other which are very tall, some others. So all of them have different features. So how does the user is going to interact with that application? Using those sliders that defines some characteristics, some features of the design. The size, the height, the number of supports, the number of legs, and the irregularity. So if we click on the support numbers, we're going to see that the species, the whole species, is going to evolve until it reaches the result desired, wanted by the user. So in that case, we want that the table has 6 legs. Yeah. So all the individuals have different features, but there is one that corresponds to a number of legs, which is the same. Okay? So we can add other criteria to define the features of our table. For example, we could change the number of legs of our table. Yeah? So once we change the criteria, the population evolves until it gets those wanted features. So if we add new characteristics, so we change the environment conditions, the species is going to evolve again. So now we are defining a height for the table. So we want that all the individuals has 52 centimeters height. Yeah? So all of them at that moment has 3 legs and 52 centimeters. So if we change again the environment conditions, so the fitness criteria, we're gonna change again and we're gonna make evolve the species, and he won't stop until it doesn't reach the criteria defined. So now all the elements has 8 legs, and now we can make them evolve again. So now all the population has different features, but there are two which are the number of legs and the height, which are the same for both. As you already know, the partner of that model will be Industria Ceramica. So what I propose as a topic for that workshop is the design of a system of ceramic components exploring the new properties that this material can achieve and afford as a surface. So what I propose is to start with natural patterns of skins as references, because the skin of living beings is a complex structure that has many properties, and I think it has big potential as a reference when looking for a surface with new properties and behaviors. So we are going to start selecting a picture using a search engine with the terms natural pattern plus fish or reptile or animal, etc. And once selected, we are going to try to identify a repetitive element which will become the basic component of our system, our tile, and we are going to isolate it from the rest of the system. So, as you can see in all those patterns I'm showing, we can identify always some basic components, but all of them are shapes, all of them have a topology, but they have many different shapes. So let me explain. So all of the basic components have the same logics, but they are repeated, changing some of the dimensions, changing some of the parameters. So, and precisely, those parameters are the ones that we are interested on. So, because they will become the genes of our species. So, what I propose is to start with that kind of references, selecting a component and trying to define that basic component and which are the variables that change in order to be applied in the whole pattern. So based on that basic component, we are going to define those variable parameters. We are going to define some other constant parameters and variables. And then we are going to translate that component to a pattern, to a system. So we are going to grow our basic component. So and here we will have to define how that growing system performs. We will have to define if those tiles are overlapped or not, and all those relations between the simple components. So once we have our pattern defined, we will have to study their properties. So in terms of visual aspects, in terms of physical aspects, for example, in terms of isolation, ventilation, etc. And we will have to study, for example, which is the fabrication process, if that implies a big cost or not. And so in a way, so the goal of that part of the exercise will be to understand possibilities and potentialities of our pattern. This is the only way that later on we will be able to define fitness criteria that we are going to propose to our customer, to our user. So it's thanks to that knowledge of our system, of our pattern, that we'll be able to define the fitness criteria that allow the user to modify the species evolution. So, and finally, we're going to define the interface and the kind of interaction for our application, following the example I showed you before. So during the workshop in Sassuolo, we are going to do an introduction to processing, and all the students interested in programming will be suggested to follow some tutorials along the module. So that's all, and see you soon. Thanks.